Milne-Eddington approximation, which is something that we will be needing again, throughout the week, really. And so there is about 54 participants, I think. We can go. This is about half an hour. I don't know, Han, how you planned it.
Yeah, it's probably a little bit less.
Yeah. So you can stop midway, or will you just go throughout it?
I can stop midway.
Okay. So as before, if you have questions, you'll be able to either ask them directly or write them in the chat, and we will be reading them. Thank you.
Shall I share screen?
Sure.
Can you all see this now?
Yes, we can.
Okay, good. Okay, so in this second lecture, I will very briefly and very maybe superficially touch on what the Milne-Eddington approximation, or maybe it doesn't even need more. It's a very simple approximation that really allows us to do some quick and dirty estimates, if you will. So let me go through on where this approximation comes from and what we can do with it. But first of all, I will summarize basically what I would like you to take away from this brief lecture, and I will summarize these points again at the end. But just to make you catch what I want to address, here are the things that I think are important. Milne-Eddington assumes constant properties with height of the line formation properties, apart from a linear variation of the source function with optical depth. Now this assumption allows for an analytical solution of the transfer equation. So it allows to set up a direct equation between the intensity and the properties that make the line appear as it is. This makes forward modeling very fast, and if you've ever done any inversions, you know that the forward solution is a part in inverse spectral polarimetric inversions that usually takes a lot of time. So this is really helpful. And it also makes things really straightforward that we have an analytic solution that we can use. This is ideal for inversions. But you have to remember always that this represents a strong simplification of line transfer. And therefore, even if you fit your observed profile perfectly in an inversion, there is a possible error. I mean, I say there's an error. Of course, if everything is constant with height, you don't make an error, but that's a very simplifying assumption in general. So there is a possible error that results from your assumptions that make up the model. You always have to be aware of that your measurements really are in the context of the model that you use. That's a very important thing to remember. So some important references. The first time that this came up, namely that you can solve the line transfer for polarized radiative transfer in the solar atmosphere in an analytical way by the assumption of having constant properties with height, was made by Uno in 56. It's certainly a paper worth reading. Then in 62, Rakowski made an extension taking into account the refractive index, the optical effect in spectral lines, magneto-optical effects in the spectral lines, allowing for a more accurate inversion of spectral lines, especially when strong fields are the subject of the study. Then the first time these ideas were turned into a practical method to determine vector magnetic fields from observed Stokes profile is the paper by Auer from 77. Although there was a paper by Jack Harvey from 72 that already alluded to this kind of option, but this is a more formal paper in that. And then if you ever want to know the details and the how quantum mechanics causes you to derive at all the equations that we use, please look into this book. It's a wonderful book. It has everything that you ever want to know and more about spectral line formation and polarimetry. But the full description is there. So Milne-Eddington, the basic assumptions, there are three. The first one is that the atmosphere is plane parallel, semi-infinite, and in LTE. We talked about this before in the lecture before the lunch break. This means that the properties of the atmosphere are constant at a given height in all directions horizontally. And this means that the source function is given by the Planck function at all wavelengths and is only dependent on temperature, nothing else. The further assumption is that all line formation quantities are constant with height. This means that the line broadening, the line shift, the polarization properties, they're all assumed to be constant over the range of height of line formation. And the third and final assumption is that the Planck function varies linearly with the continuum optical depth, namely that the Planck function B can be written as some constant B0 plus a second constant B1 times the tau C, which is the optical depth at continuum. And we can bring out the B0, and the beta is then B1 over B0. Now, let us recall the equation of relative transfer in a semi-infinite plane parallel atmosphere. It can be written in this way, with the optical depth defined in this way, where alpha is the absorption coefficient. And since, to remind you, since optical depth runs opposite to the height scale, it introduces a minus sign. So we have the aspect, mu, times di d tau is I minus s, which is the reverse of signs when you write, compared to when you write down the equation of transfer along a ray in the direction of the ray. Then again, like before, we can write the emergent intensity at the surface, tau equals 0 at cosine of theta mu in this way. This is called the formal solution for the semi-infinite atmosphere, 0 to infinity, because we integrate from the surface till the depth of the atmosphere. Then we apply the Milne-Eddington approximation and write that the source function is equal to the Planck function is B0 times 1 plus beta times the continuum optical scale. Now, if we have a line overlapping with that continuum, then the total optical depth is the sum of the continuum plus the optical depth in the line. And now we can write this and we can do this because the line properties are all constant with height. We can write this as a ratio eta of the line core opacity over the continuum opacity times normalized absorption profile, and we come back to this absorption profile a little bit later, times the continuum optical depth. So the continuum optical depth is the total optical depth divided by 1 plus eta phi. Now in this integral, the integration is of course over the total optical depth, because we need that to calculate the emergent intensity. So now if we replace this source function with the Milne-Eddington approximation and include the overlapping line, we can write the source function as B0 times 1 plus beta times the total opacity divided by 1 plus eta lambda. And substituting this expression into this formal solution, we can actually calculate the exact solution. And it is this. The emergent intensity is B0 times 1 plus beta mu divided by 1 plus eta phi. So we can stop here briefly if there are any questions.
There's no questions in the chat box so far. If anybody has any, you want to unmute and speak up. It might be okay for now.
Okay, so to recapitulate, the Milne-Eddington approximation is a very simple one in the sense that you assume that all line properties are constant with height, which allows us to make this assumption, write this. And we assume that the source function varies linearly with the continuum optical depth. Those two things. And of course, there's a plane parallel atmosphere, and we assume LTE in this case. So when we make this assumption, and of course, this is a fairly limiting assumption. But it's not too, I mean, you can do the exact calculation and compare how limiting this is. And it's actually surprisingly not so bad. But you really have to understand that you are forcing your solution, your measurement of physical parameters, basically in the straitjacket of this assumption, right? You are bound, your values really are tied to the assumptions that you make. So let's talk a little bit about the line profile. For spectral lines, and it goes a little bit too far to talk about the theory of why spectral lines are not delta functions of wavelength. They are really broadened. For the very first reason is that their lifetimes are finite. So with
and there's a question on your previous section before you move on. Can I interrupt you real quick?
Okay, yes, sure.
So the question is, isn't it a stretch to say it's LTE, B0 is a constant, and it could be anything? Could you expand on this?
Well, in the theory, B0 is just a number, and it is not derived from anything. So when you derive from your observations a value for B0, you have to understand what that means. It is not just anything. It is really a value that is related to the physics. And you can derive from it via the Planck function, obviously, and the wavelength at which you observe. You can derive from it a temperature at the line formation height. Now, what exactly the geometric height is that you measure this, you've thrown away with this assumption. With the assumption that everything is constant with height, you've thrown away your ability to determine at what height this temperature occurs. You just know that it occurs somewhere in the atmosphere and where the line forms. But without any additional constraints, you don't know that from this analysis. So it is not just a number. In this equation, yes, it appears just as a number. And for the examples that we calculate, we can basically set it to 1, meaning that the source function in this case is unitless, it's just 1, and that the variations that we determine by the applying the spectral profile are just relative variations. But it's not just a random number. So I hope this distinction is clear. So if you do observations and you put them in terms of this theory, you determine an actual value of properties in the atmosphere. From that, you can determine the temperature with the Planck, given the Planck function and the wavelength at which you observe.
Rebecca,
so
do you want to chime in directly?
Sorry?
Rebecca had some follow-on comments. I'm just wondering, it might be easier for you just to speak up.
Oh, it was actually a genuine question. I never thought of Milne-Eddington as an LT problem. It's so heavily simplified. But as I understand, at least from what you said, it's the post-interpretation of B0 that you can compare to the Planck function and get a temperature from it. That's what makes it LT. But in the Milne-Eddington model, it's purely a fitting parameter, right?
True. So it's basically the value of the source function at the height. And, and if LTE is not applicable, then it means something else. Then it does not directly relate to the temperature.
Yeah. Okay, I understand. Thank you for the clarification.
Yeah. No, you're perfectly, that's certainly right. That's true.
And there's some follow-on questions. So if you have a gradient in the source function and you assume the source function is determined from the temperature from Planck's law, don't you assume the gradient of temperature in the atmosphere?
When I write this down, then yes, beta is a given number. In the inversion, you determine beta by fitting, and exactly the exercise that Ivan will bring after this one is determining in part beta. And so you determine then the gradient of the source function, or of the temperature in this case, from observations by determining what the best value is to match your profiles to the observed profiles.
So it seems like there's a bit of back and forth in the chat window, but maybe you should go on, and this could be something we take to the Slack channel.
Okay. So again, just if we are following the equations and we are aware of the assumptions that we make, then we predict that the emergent intensity is this function of what will turn out to be 5 parameters of the atmosphere, 5 values of physical parameters in the atmosphere, namely the B0, the beta, the eta, and 2 values that determine the line profile. And so let's go a little bit further in that. So as I said before, absorption coefficient is not a delta function. It is it has a certain width. And the very first reason that it has a certain width is the fact that the lifetime of the levels involved of the excited level is actually finite. And with the uncertainty principle, this means that the energy of the upper level is also not exactly specified, and therefore the wavelength is not exactly specified. So if I have an ensemble of atoms, then the line will be broadened. Then, of course, the line is, there's interaction of the excited atom with other particles. There are particles that perturb the energy state with elastic collisions. And these collisions also broaden the upper level. And finally, these atoms are moving randomly with an average thermal velocity of a given amount of kilometers per second. And this also broadens the line just by Doppler shifts in random directions. So when you follow all this through, then in the atomic frame, the line profile is described by a Lorentzian. In the observer frame, this Lorentzian is then convolved with the velocity distribution, the thermal velocity distribution of the atoms that give you the line. And the result of this convolution is that the line profile, and again, I use frequency and wavelength interchangeably because there's a one-to-one correspondence, right? But the line profile that results from this convolution of the Lorentzian with the thermal velocity distribution is a voigt function, usually denoted by the uppercase H. And this voigt function is a function of the damping parameter, and the damping parameter is actually a function of the lifetime and collisional broadening and so etc. can be translated into a lifetime as well. So this is the proportional to a inverse lifetime. And a Doppler broadening. And Doppler broadening is given by the 1 over lambda 0, nu over c, times the thermal velocity, 2 kt, where k is the Boltzmann constant, temperature, and m is the mass of the atom. So this this voigt function has two parameters, basically. It is this gamma that determines the damping coefficient, and it is the thermal broadening that determines the scale on how actual wavelength translate into unitless Doppler units in the Voigt profile. So given a wavelength scale and these two parameters, delta nu Doppler and the damping coefficient A, completely describe the line profile. This is a plot. Note that this is logarithmic of the normalized Voigt function. When you integrate over wavelength, this should be 1. And this is the Voigt function on a logarithmic scale as a function for different Doppler or damping widths. This is 0.1 and the smallest one is 0.4. You see that in the line core, the Voigt function approximates Gaussian, as plotted here with the dashed line. But in the wings, these are called the broadening wings. So now we have the Milne-Eddington solution from 2 slides before, which is B0 times 1 plus beta times mu, divided by 1 plus eta, the line strength relative to the continuum, times the absorption profile, the normalized absorption profile, which depends on the damping coefficient and the thermal broadening. And so now your intensity depends on 5 parameters listed here in the atmosphere at the line formation height. Just let me show you, and Ivan will come back to these graphs in the exercise that he will start after this. This is the line profile as calculated with the Milne-Eddington approximation. So just basically, I calculated, given the 5 values of these parameters, although I've scaled B0 to 1. Or actually, it's 1 over 1 plus beta, so that it's constant for all profiles. For these values, where I varied the damping parameter from 1000 to 1, and these are presented by the 10 blue lines. Here I varied the lines, the gradient of the Planck function, beta, from 0.1 to 4. And you see that when the gradient is stronger, the line core senses a bigger difference between the temperature in the a bigger difference in temperature, as is clear between the differences intensity in the line core and the continuum. And here I varied the thermal velocity from 1 to 5 kilometers per second. And you clearly can see that the line varies accordingly. Again, in summary, Milne-Eddington assumes constant properties with height, apart from a linear variation of the source function with optical depth. It allows an analytical solution of the transfer equation, as I've shown. This makes forward modeling very fast, and it makes the implications very direct. This is ideal for inversions because you know what you're doing and it's very fast. But, and this is a very big but, it represents a strong simplification of line transfer. So you have to be aware of that. And even if you fit the observed profile perfectly with your inversion method, and mathematically you do everything correct, physically you're making an assumption, and there is a possible error that results from the assumption of this simple model. So yeah, that's what I have. Any more questions?
I have a question.
So
it seems like, how I understand that Milne-Eddington approximation is, it just gives us a closed form for the source function,
correct.
which gives us an analytic solution to the redshift transfer equation.
Correct.
Which then we can fit to the data.
Yes.
And then from these free parameters that we fit to the data, it comes all the physical information about the atmosphere.
Correct.
But we had this discussion in the chat about that if you have a changing source function with height, then if we're in LT, we would assume a gradient in the temperature.
Yes.
But we have only one temperature. So in a way, it's...
No, you get both, right? You get B0 and beta.
Yes.
So you get the temperature basically everywhere.
Function of tau.
As well, yeah, yes.
Yeah.
But you don't know where that is in height. That you've given away.
I see. Okay.
A question yeah, I have a question. Oh,
yes.
Yeah, maybe I'll just go ahead. I'm just wondering, because you're talking about this, say, constant profile at a fixed height. You're looking at spectral lines, say at one pixel, right? At
yes.
one fixed spatial position.
Yes.
But wouldn't that be a reasonable assumption? Say if you just confine, because it's confined in space. Say locally, it is a zeroth order approximation, a constant. But then this constant can change from location to location.
Well, it is a fair approximation, and it is a reasonable, perhaps, in cases, but it's not an. It is an approximation, right?
Right. Yeah.
I mean, in a sense, it is not even a consistent approximation because you determine a gradient of the source function, which in LTE means a gradient of the temperature. Now, if the temperature has a gradient, that actually the Doppler broadening cannot be constant because it depends on the temperature via the thermal broadening. So in that sense, it's not even a self-consistent approximation.
So in other words, the spatial dimension is somewhat kind of omitted, or you're talking about the infinite space, right? So locally, certainly that's not the case.
It is an approximation in the sense that what you get is some kind of a, you can call it an average, although what exactly that means in terms of how it's averaged is not clear, but you can get some kind of average value of the line properties over the line formation height. It is not the value at one specific height. It is really over the line formation. You measure some kind of average. Weighted, how it is weighted is not clear, obviously.
But I have I was confused by this discussion. I sort of understood that Chiang, I don't know the pronunciation, was talking about a spatial distribution in the XY plane, like on the surface. I'm not sure
sure.
if I interpreted that well.
Right, yes.
Oh, sorry, then I misunderstood. I understood. So yes, you get values that are different for every XY location. And you see that typically a Milne-Eddington gives you a fairly smooth map. So there is some physical sense in the observation, in the inversion in that sense. It's not like a random value that you get at each pixel. It does make sense, but the difficult part is in the exact interpretation of what exactly you are measuring at each pixel.
Thank you.
I have a question here.
Yes.
Yeah, so this approximation allows the source function change with the height and the temperature gradient.
Yes.
Also, you mean the constant properties with the height. What do you mean the properties here? What are the key things here? I know this complexity actually. That's what we want to find out. So when you're assuming properties constant with the height, what are the properties do you exactly mean?
Well, what you mean is the assumption is that the properties of the line, the thermal broadening, I mean, it's a square root of t, so it doesn't vary fast with height, right? So you're assuming that all these properties are functions of height that vary slowly enough that over the line formation height, which is typically maybe 200 kilometers, are constant enough that you can make this assumption.
So such as the density, composition, those kind of things?
No, so the really density, you don't care. Density does not enter here, right? The source function is just a value. It's not, yes, Ivan.
Can I maybe try to explain in a different way? So as Han showed us at the beginning, in order to really properly calculate everything very consistently, we need to know opacity and emissivity everywhere on a height grid. And there are a lot of variables that enter these things: pressures, densities, electron densities, velocities, and so on. But what the solution of the radiated transfer equation cares about is just the source function at given wavelength, calculated or given on a grid of optical depth on that same wavelength. And these two quantities give us the final solution, which is intensity. So this Milne-Eddington is a way to simply get away with as little parameters as possible to get something that makes sense. So that is why we always say that we don't care about densities, we don't care about these things. They're somehow hidden in these calculations or actually not even calculations, in this given tau grid and so on, but we have no way of inferring them from this. I don't know if that makes sense.
Well, yeah, I guess helps a little. Still, I try to understand what is the complexity here. If you does introduce those complexities, such as assuming non-constant properties. So what are those key properties that does affect this inversion results? Such as variation of the abundance or variation of the pressure. I just guess. I don't know.
So if you want to do an accurate, in the sense that as close as possible to reality inversion, you have to account for all of these things. But the assumptions of the Milne-Eddington are such that you throw all of those overboard. You ignore them, and in a sense, you actually hide them just by the way of you write the equations. You hide the value of the Planck function. You hide some of that in in assumption of the Planck function. But what you lose is basically that your model loses the ability to determine at what height in the atmosphere you are.
Yeah, thanks.
If there are no other questions, I have a comment. That is, on Friday, you might have seen in the program that there was like half an hour reserved for discussing a research paper. And actually, I think that we have agreed on this paper, which will touch upon this same questions that we had today. You know, how much a Milne-Eddington approximation is, how good it is, you know, in reproducing the properties of your atmosphere. And this was done by using modern MHD simulations and proper spectral synthesis in those. Of course, we're talking about photosphere here. We're not touching anything but the chromosphere because that will not work. So that would be probably good to, you know, to get this discussion going again. I will be sending the link to the paper later today or tomorrow. You know, I think it's nice if you have heard these things before you go and read the paper. So maybe at the end of tomorrow afternoon, I will send it.
I want to confirm one thing. It might be dumb at this point. So all your fitting, so this is for Han. So all your and Ivan. So all you're fitting for here is for the source function, obviously. So, but your temperature, is your temperature actually changing? Like not reality, but like in your inversion, is your temperature actually changing with depth or not? Or it's like, I think I'll just circle back.
There is no temperature.
Yes, my question. There's no temperature.
There is no temperature. And this is the discussion that we had before. There is just a source function on the optical depth. And we can choose to call it temperature. And as you have seen in chat between Valentin and Rebecca, you can actually completely change this and make the source function drop off exponentially and not linearly. And then it's still analytically solvable. And then you definitely cannot call it temperature because this exponential approximation comes because of something else. And I think it's misleading to call this temperature unless we agree upon this at the beginning. So Han said in his lecture at the beginning, okay, we're going to assume that this is LT, so then it's temperature. But in general case, what enters the equations is the source function. Sorry for hijacking this.
No. This is good. I was totally lost in that. I think I was totally lost.
I can actually comment again as a very outsider in this. I have the same questions, and so when you do these inversions and fitting and so on, we are forgetting about the actual intensity values, right? You put everything to the continuum, which is 1, whatever units, right? It could be a very hot atmosphere, it could be a very cold atmosphere. You really don't care too much. You will find, you know, at the end of the day, why we're here is because of the magnetic field and so on. But we don't know whether that is, you know, what kind of temperature could be attached to it, even if it were an LTE.
That's a good point, Jana. And if you wanted to relate it to a temperature, and it was, again, the repetition of the same discussion, you would have to first calibrate that source function and source function gradient to what they mean in terms of real temperature. And then you could probably extract somewhat meaningful temperature values from them, but with a limitation.
Yeah.
Milne-Eddington is essentially a series of line fitting parameters plus a couple of actual physical variables, which are the magnetic field when we see the magnetic case tomorrow and the line of sight velocity. But everything else serves the purpose of fitting the line. And it's really hard to extract meaningful thermodynamical information from it. Mm-hmm. At least that's my experience with Milne-Eddington.
Another short question. Do we have to require that the azimuthal angle in the fitting should be pretty small, or say the mu is close to 1 to make sure that the fitting is sensible?
No, I mean, the equation is very clear about how mu factors into the intensity. So you of course determine mu is a given, it's not a free parameter.
Yeah, I know.
It's a value
So
that you
what I'm curious, if the mu is pretty small, say the observation is pretty close to the limb, would that make the fitting gives you some useless information?
I mean, that's generally the case for for limb observations, because well, for one thing, the density in a gravitationally stratified atmosphere varies much more strongly in the vertical direction than in the horizontal direction. So once you go towards the limb, you're actually averaging over several granules or whatever you. So it becomes more confused.
Yeah, thank you.
Okay, so I think that concludes the lectures for today. And so